Hello. This is our makeup lecture for week number 6 of ELE452 Fundamentals of Medical Imaging course. So it's about to have some idea of the state of art ultrasound imaging systems used in medical centers. In the week number 5, we have covered face to face in the lecture room. We have covered the physics of ultrasound and some general theoretical concepts. Now it's time to have an idea of how these theories are applied in today's state-of-art systems utilized for ultrasound imaging modalities in health centers. So this is called hardware, but more general instrumentation aspects of the theoretical information. So this is a typical ultrasonic systems, one of the systems used in the hospitals or ultrasound imaging centers. Those systems are mobile. You can uh, carry them by the patient's bed or nearby the patient by using the wheels, and it's all computers and electronics and screen monitors, printing device, etc. All the stuff is accumulated on this big combined system. So the doctor is in charge of directing or controlling everything by the system. Usually, this doctor has a kind of auxiliary health personnel to help during the imaging phase, and the patient is usually lying down in a bed next to this instrument. So in the figure on the left, you see the front view of this system with the screen and keyboard, trackball, and other related equipment with crucial electronics and stuff like that. And the probes are marked with blue, colored, encircling, etc. These probes are the actual signal sensors in touch with the patient body to receive ultrasonic signal information. The complex signals from the patient are acquired, and then uh, necessary calculations were made to represent them as an image on the screen. So these are connected to the electronic boards of the system. Here is a typical ultrasonic image, usually on a piece of printed thermal paper, or they can be stored or transmitted via electronic means by means of equipments, telemetric equipments. If you see the image, uh, the top of the image is where the probe is placed. So the signals are transmitted from the probe towards the inner part of the patient, and then they are reflected back, um, usually more than one times, so that each boundary and acoustical properties like acoustical impedance of the different tissues, can be calculated by the system and displayed as a grayscale color. So with this color distribution, anatomically, the expert physician can handle any soft tissue inside the body and have an idea whether everything is normal or something is abnormal, etc. So on the image with handwriting, yellow arrows represent the propagation of the ultrasonic signal, and through the boundaries, we experience this propagation exhibits transmission and reflection, and everything's assumed to be orthogonal. So there is no, let's say, um, big angular transmittance and reflections from and to the organ boundaries. If you look at the system's electronic components, you see the patient is at the bottom of this slide and probe is touching to the body. A special ultrasonic gel structure to avoid the air bubbles between the patient's skin and probe is uh, smeared on the probe for good acoustical signal transmission. And this ultrasonic signal is sent by via pulses, okay? So both transmitter and receiver received signals are in the pulsating modes. So these pulses are decoded and they are amplified and then decoded according to its phase or other related parameters to form the image towards the towards the up part of the slide to the right. So from one of the auxiliary books related to this course, this is the, let's say, some explanation of the general block diagram. So if you look at the details of the system, in the transmit node, the system sends signal and the transmitter pulses are turned off, and then another receiver circuitry is now connected to the circuit to receive and amplify the reflected signal, which is much smaller than the transmitted signal. So there's a kind of multiplexing. Multiplexing is done, here it's shown with a rectangular box. Okay, maybe I can, yeah, highlight it. Transmit and receive switch. So from the left side, there's an oscillator creating over 100-volt peak pulses of ultrasonic pulse generating mode. This is the transmit moment. And then the received signal after a certain time, this multiplex switch selects the received pulses to send in another channel to be pre-amplified and then processed and then analog to digital converted, then stored in the computer environment or digital environment, also has the display as well. So you can either see everything real time digitally on the monitor or screen, and at certain moments you can save as a photo or image. You can send or print out or everything you can do with a computer infrastructure. So this is the moment of the signal path of the received pulse from the patient. These blue arrows show the path of the received signal, which is much more smaller in amplitude. Therefore, it should be amplified and some other unwanted frequencies should be filtered out. In ultrasound imaging, like almost all imaging techniques, except nuclear imaging that we will see later on, the source, the energy source, producing the actual energetic waves is outside the body. The source is ultrasonic wave source. Here, that's an oscillator and piezoelectric crystals creating mechanical vibrations. So the energy is transmitted like a mechanical vibrational way. And the transmitting energy is in pulsatile form, where you see the period of transmitting moments with some amplitude I and duration tau, and tau over the general period is called the duty factor of transmitting. So basically, these systems are time-shared distance. At a certain time, tau transmitter is active. Beyond that tau, up to the first period, receiving part is in duty to form the image. In medical ultrasound imaging systems, ultrasonic sound pulse generator touches the body, as I said, and sends ultrasonic waves. Those waves should travel with minimum loss. So that's the reason ultrasonic gels are used. And the waves propagate in the tissue. During this propagation, both signal attenuation occurs per distance, reflection and transmission also occur at the boundaries. So from the time delay of the signals, you can determine both of these unknown parameters and reflect on the display screen. Here's a little block diagram of any, again, an ultrasonic system. In the block diagram, you see at the center of the system, a central processing unit or CPU or is a kind of computer. In today's systems, very specialized CPU and computer peripherals are in duty to control everything because those data size and real-time operations require a complex architecture. This central control unit controls everything from probe electronics to keyboards, cursors, printers, disk storages. So basically, a powerful PC is embedded in ultrasonic systems, as well as not shown in this figure, transmitter and receiver, either wireless or cable Ethernet type of hospital informatics systems connections are available in these systems. So here are some probes. Those are the most important parts of the ultrasonic systems. Transmit and receiving energy is done with these piezoelectric materials. So these probes do have a cable. One side is a connector with many, many pins, up to 512 by 512. And the other side is composed of, again, that matrix structure of piezoelectric crystals. So this is another type of probe. So you can arrange the alignment or the focusing of any ultrasonic waves in multi-channel piezoelectric crystals. Here, each little element of the two-dimensional array represents one piezoelectric crystal, and its size may differ according to the sensitivity or energy distribution pattern of selected probe. So that's another type of design criteria. So the simplest, most basic or popular or widely used crystal is called PZT. This is a kind of special uh, material, and this material's so-called PZT4 is actual ultrasonic vibrating part. The other one is like a mechanical backing, so that its ultrasonic energy cannot reflect back to the instrument. Rather, all of them reflects towards the patient. And the other stuff is like protective parts from outside effects, as well as you can clean these things, sterilize these things. So you have to not to damage that PZT4. They are used for covering and protecting it from mechanical stuff. And you can have some kind of circular or convex or other geometrical things for a good ultrasonic energy transmission pattern or propagation pattern. You can, for example, here's a kind of very simple 5-element uh, piezoelectric array, let's say. Okay, if you can energize or activate each component at a certain time so that their waves are superimposed at some out of focus points from the body. So you can target the most selected or the most sensitive part from the tissue so that you can focus that signal from any part, any point part of the patient by using electronic delay equipments. So you can give delays to transmitted pulse so they focus on special part of the body for increased sensitive investigation as well. Okay, so this is another powerful of uh, different channel activation or multiplexing different piezoelectric crystals at certain activation patterns. For example, in that particular illustration here, you can activate the bottom gray colored elements at certain times so that their wavefronts are not linear parallel to the crystal array. Rather, they are like convex or having some spherical boundaries. This is also possible. So that according to the needs of the investigation, you can electronically adjust ultrasonic pulse pattern. After the probes, this is the user interface part, which is the console of the instrument. The console consists of a general structure of a computer control, but it has also has some kind of ultrasonic signal distribution or amplitude equalization, or from the screen some kind of image processing or on the screen calculation apparatuses as well. For example, you can measure the distance of 2 points on the image to have an idea of the certain lesion or part of the body, the dimensions, volumes, or surface areas of these kind of organs for medical diagnosis purposes. So these controls are also embedded in the big keyboard console of the equipment. This is one of the SPECT family, very brief SPECT family of available commercial devices. For example, 17-inch LCD screens, some touch screens for keyboardless or special control equipments, 5 probe ports, so that you can have all ports connected and utilize anyone you are interested. You don't have to switch or unplug, replug, or any, you don't lose time. So these are multi-probe equipments. There are many different kind of softwares for image processing, equalization, just to increase the signal to noise ratio or contrast to noise ratio according to the um, examiner's requests. Also, Doppler abilities or other um, three-dimensional or um, video mode recording of these instruments are also possible. DVD storage, USB ports, DVI ports, those are general informatics equipments to share the resultant images with other computers, remote centers, or other doctors. With, those are the strengths of the uh, devices. The imaging modes of these equipments are numerous, okay? One dimensional or two dimensional or even three dimensional or motion mode, color flow Doppler, those are available in today's expensive and new systems. 2D systems are the default imaging modes, which I had already shown a sample. Two-dimensional depth equation is displayed on the screen. You can have motion mode, which means if your organ is moving during the imaging, like your heart, your lungs, or other parts of the body, blood, for example, you can trigger the image at a certain time so that take the image every time at the same moment of that moving organ. So that mostly used in heart or electrocardiographic investigations. Color flow Doppler means that you can examine the blood flow, whether the flow is okay within the velocity, speeds, and flow amount of blood, or not okay. So you can detect some kind of occlusions in the veins or arteries for the health risks. This is the most up-to-date, newest, nicest properties, three-dimensional imaging. Although it's not, let's say, the quality of the images are usually low, you can have some kind of three-dimensional structure of the internal body. For example, this is used in fetal imaging, baby in the abdomen of the mother, for example. So those are the state-of-the-art system properties, okay? From the basic up to the newest. Well, a few things about the safety in ultrasound imaging, although it's the safest technique. There is no ionizing radiation, everything's okay. Well, still there are some risks, very low, but non-zero. This is an electrical equipment, so you have to take care about the electrical things. You have to calibrate this equipment because you are sending some energy to the body. That energy is really low, but you have to make sure that you are sending that low energy. So never ever exceed some safety limits of this energy. Very long time, hours and hours of course, imaging time not possible, but it should be kept in mind that excess energy should not be sent to the body. If some of your, devices, calibrations or properties are not finely tuned, you can send excessive energy. That excessive energy starts to heat up the body. If you warm the body up to some degrees, even if you have a few very small regional heating, that's bad for the cells over there. Well, the chances are really low, but again, not zero. So there are many studies and works about the safety limits of different organs at different frequencies of ultrasonic waves. You have to at least be at least 10 times less than the predetermined level to be on the safe side. So this is another issue of signal attenuation. You have to make sure that, of course, if you send too little energy, then that means it will be absorbed in a shorter distance. You cannot see what's present in the deeper layers. So there's a compromise. Okay, so you have to keep in mind that for all different tissues, there's a parameter of absorption coefficient, so that you have to know your signal as well. Cavitation, those things happen at the very extremes, okay? If you send big amounts of energy, you locally start to vaporize water in a very small microscalic range. Those things are sometimes used in to destroy some cells, cancer things, or some plaques or unwanted things in the body. But you have to be very, very cautious about that. Especially ultrasonic energy deposition is used to break stones in kidneys. So you have to be very specific and careful about the location and amount of energy sent to the body. Normal ultrasonic waves do not have this risk, but still you have to be very careful. For some blood vessels and in fluid environments, cavitation occurs, and this is not desired, so you should be very cautious. Of course, there are some limits of safety of these aspects published by World Health Organization and similar imaging organizations related to energy radiation. And according to the frequency of interest, the limits change from person to person, age to age, in general, public health or professionals, etc. Again, you have to specifically, very carefully follow these limits when you are a designer as well as an application engineer of these kind of instruments in medical fields. So we come to the end, and I have to acknowledge some resources. Those are our previous textbooks. Some of the information and figures were over there. And thanks for watching my online lecture explanation.